Hey guys, welcome back. Building off of yesterday's lesson where we learned the product rule, which is the derivative of two functions that are multiplied together, today we're going to learn about the quotient rule, which is two functions that are divided by one another. So we are going to go through not only discover what the quotient rule actually is, this is something that you'll have to know and remember moving forward. But we'll also go through a couple of different examples and things that we should look out for, maybe some tips and tricks to try and get through these as easily as possible. So, without further ado, if we do have a function of the form f of x divided by g of x, then its derivative can be found by this formula. So, this is something that you should absolutely write down, highlight, box, and star. One of the more important formulas or rules that we'll come across, certainly for this first term or first semester that we're together. And this is not something that you'll be given on a test or an assessment or anything of that sort, so you will have to know this one. It is definitely a little bit more complicated than the product rule. The product rule was not, I wouldn't say simple or anything of that sort, but maybe just a little bit more straightforward and kind of less to remember. And so this one, while it does have a couple of extra parts and some things I'm going to want to point out for you in just a second, it's actually not too bad, especially if you compare it to the product rule, because what we see is that the numerator, f prime of x g of x minus g prime x f of x, is almost exactly the same as the product rule, except we have a subtraction instead of an addition, which is a big part because we know that that subtraction may force us to eventually distribute the negative into a quantity. So that's something that we're going to look out for. Okay, so quotient rule, there's a minus there. And then the biggest difference here is that this whole denominator is divided by g of x squared. And so one really important piece here is that that is just g of x. It's the original denominator squared, not g prime. That's a common mistake to put the derivative of g down here and square it instead of just the regular function g of x, whatever it might have been. All right, so this is the quotient rule. We are going to work through a couple of different problems. And so just a couple of quick notes. Again, why are we doing these? There are types of models and functions out there that are supposed to analyze and model, real world situations. As we look at different situations, those functions becomes more complex, and they take on different forms. And sometimes the form of a model might be a quotient of two or more different types of functions. And so this is another way for us to get to the rate of change, the instantaneous rate of change, or the derivative of that function. And so here is our new rule, the quotient rule. And then finally, I know we're using f of x and g of x within this rule, and we're just kind of splitting up the numerator and denominator functions as f of x and g of x. But please remember that the function itself could be called just f of x or called just g of x. These are just notation markings, or there's ways to denote that, hey, I have a denominator function and a numerator function, and this is where the pieces fit together. Okay. So really quickly, a couple of things to look out for. What types of functions are f of x and g of x? So we're going to be looking at functions that are quotients of algebraic functions, exponential functions, maybe radical functions get in there, and certainly trigonometric that are going to come in. Eventually, when we learn the derivatives of, different exponential functions and logarithmic functions, we'll add those in as well. But it's important to note, because what happens is, depending on the types of functions, simplifying the final answer may require more steps. And so what I mean by that is, typically when you have algebraic functions and or radical functions mixed together, anything that really requires simplifying, such as combining like terms or factoring out, or maybe simplifying a complex fraction, those things come out a little bit more when you have certain types of functions working with one another. And typically that's your algebraic and radical functions that increase the chances of having to simplify more. When you have exponential or trigonometric functions, these problems are actually a little bit easier as long as you know their derivatives. And we'll see an example of that. And then finally, if you ever come across a function that doesn't necessarily look like a fraction, maybe it's a trigonometric function, which we'll talk about at the end of the video. We'll actually, at the end of the video today, we'll be able to know all 6 trigonometric derivatives. So this is basic trigonometric functions: sine, cosine, tangent, cotangent, secant, and cosecant. We'll know all those by the end of today. Or maybe there's some type of negative exponent that allows you to turn that function into a fraction. Is it easier to use the quotient rule from there as opposed to maybe using the product rule or some other type of rule that we'll learn later down the road? Just things to look out for, and this is certainly a way to do that. All right, let's jump into an example and we'll go from there. So here's my first example. Find the derivative of the function x plus 1 divided by x minus 3. What I notice up front is that this fraction, or this function, cannot be simplified any further. There's nothing I can do to x plus 1 over x minus 3 to make it easier on myself to derive. This is definitely, you have to use the quotient rule in order to derive this one. So first thing I'll notice is that there are also algebraic functions. So there's two algebraic functions divided by one another. I'm going to look out for things like combining like terms or factoring out common terms when I go to do my simplification process. So I'll break up the function into f of x and g of x, right? And again, that's just a numerator function and a denominator function. What I first want to figure out throughout these problems, at least initially, so I can start getting the hang of it once I get used to using the quotient rule, is, well, what are all the pieces I need, right? So here's our formula again. And so what I notice is that I actually have almost everything that I need. I just need the two derivative pieces. And this is very similar to what you would have done with the product rule as well, right? You have f of x, you have g of x, but what you need is f prime and g prime. So that's the first thing that we're going to find. And luckily for this first example, those derivatives are really easy. They're both equal to 1. The 1 and the minus 3, their derivatives are 0, so they'll go away. And then the derivative of x, the first, is just 1 itself. So the derivative of f and g are both equal to 1. So now I have all four of my pieces. I'm just going to plug and play in here and see what comes out of it, all right? So when I plug these values into my formula at first, here's what this looks like. You've got your f prime, g of x stays the same, minus 1, and then notice that I'm keeping x plus 1 in parentheses. That is a quantity. I'm subtracting it, and therefore I know that I'm going to have to distribute that negative in once I go through this process. So again, very important to remember that you're going to have to distribute this negative into x plus 1. If we don't do that, obviously we're going to get the problem wrong, so we want to just be careful with that. All right, so once I do this, I notice that the last part is x minus 3 all squared on the denominator. Again, that is just g of x, not g prime, x minus 3 all squared. I don't have to expand that out because expanding it would actually make it less simplified. All right, so x minus 3 squared is just going to stay that way. And a lot of the times for these problems, that's how it's going to look. The denominator is going to be squared unless that can be simplified with the numerator in some way. So here's my next steps. And again, you can see that that distribution of the negative come in. Once I do that, I have some simplification on the top. X minus x will go away. Negative 3 minus 1 will become a negative 4. And the x minus 3 squared will stay on the denominator. There's example 1. Example 2. So this one is going to require much more simplification than the first one. And so this is a good example because it shows you sort of some of the things that you're going to have to look for and some of the things that you're going to have to do. So this is all techniques that you're aware of, or we might have even done in class at this point already, but you have to be really careful and very patient as you go through these problems because there's a lot of different little pieces that you could get wrong as you move throughout these problems. So just making sure you're taking your time and understanding the process is really important here. So here's my function, the square root of x minus 1 divided by 3x plus 2. I notice that I have a radical function on the numerator and then just an algebraic function on the denominator. Again, that mixture should at least red flag you to say, hey, there's probably going to be some extra simplification here. Additionally, when I find my extra two pieces, right, the f prime and g prime, I notice that one of the derivatives, specifically in this case, f prime, the derivative of the numerator, is equal to 1 over 2 root x, which is a fraction in itself. Whenever we have a piece of our overall function, like the numerator or the denominator is a fraction itself, that again is a red flag to say, well, if I have a fraction as part of my overall rule or overall formula, and I'm putting that into another fraction, then I'm going to have some type of complex fraction, a fraction over a fraction. And that is going to require some additional simplification as well. And so you see that red box up there, that's something that we're going to have to work towards as we move through this problem, eliminate the complex fraction. And again, I just want to note, just so I don't want to confuse anybody. I've said this enough, but that's fine. We can say it as long as we need to. The overall function is f of x. I'm using f prime and g prime. Notice I didn't put the of x there because I didn't want to get confused here. That's just saying, hey, I've got a numerator and denominator. This is the derivative of the numerator. This is the derivative of the denominator. This is not the derivative of the overall function. Okay, so these are just my pieces that I'm using. Shorthand, it's very typical that you just use f prime, g, f within these formulas, just so you don't get too confused or mixed up with your overall function. So I've got my pieces, I've got my formula. Let's see what comes out of it. So here's my first step, just plugging everything in. Again, making sure that you're organized with this step because this controls everything else. Okay, so I've got the 1 over 2 root x, that's my f prime. The 3 is my g prime, and I have my other functions. And you see in the denominator 3x plus 2 all squared. That stays the same. Next step is to distribute these pieces in because I eventually want to combine like terms if there are any, simplify any complex fractions, or factor any common terms out. So the next step I'll do is I'll take the 1 over 2 root x, I'll distribute it into 3x plus 2, and I'll take the negative 3 and distribute it into the square root of x minus 1. When I do that, here's my next piece. I'll give you a second to look that over. You see I did a little bit of simplification. The 2 over 2 root x just becomes 1 over root x. I distributed both a negative 3 in, so it becomes a positive 3 on the end. And so the next step, if you see this last line on the top here, I didn't show this, but I did simplify and combine like terms with the front term here, 3x over 2 root x, which is really 3x to the first over 2x to the 1/2. And so those exponents do cancel, or reduce with one another. And so this term right here, 3x over 2 root x, actually becomes 3/2 the square root of x. And so 3/2 the square root of x minus 3 root x is a negative 3/2 root x. Everything else stays the same. Here's my positive 1 root x and my positive 3. The only thing I have to do now, I have that complex fraction. So how do I simplify or eliminate the complex fraction? I need to find a common denominator of the numerator fractions that I have. And so how do I find a common denominator? Well, I just multiply all the denominators I have together. So I have a square root of x, a 2, and then technically a 1. And so the common denominator here is 2 root x. And so I'll have to make sure that everything is divided by 2 root x. And you'll see that the 1 over root x just needs you multiply both the numerator and denominator by 2. The middle term needs to have an additional square root of x, so I multiply both the top and bottom by the square root of x. That changes the numerator to just 3x, so the square root of x multiplied by square root of x just becomes x. And then finally, for the last term 3, it doesn't have any denominator, so I'll have to multiply both the numerator and denominator by 2 root x. And so that's why you get 6 root x over 2 root x. From there, this is all one big fraction, and I can combine the numerator to become this fraction. So I just combine the numerators there with the singular denominator. And the final step is to use your multiplication by the reciprocal. And really what that does is it brings the 3x plus 2 squared up to the numerator's denominator, and I get my final answer here. So a lot of simplification there. I think this is one of the more difficult problems, not necessarily because of the calculus that you're using, but for some of the algebraic simplification. So take a moment if you need to, pause the video, jot down some questions if you have them, or just try and work through this one a little bit more. All right, example 3, this one will go a lot faster. So this is finding the derivative of h of x equals 3e to the x over cosine x. I notice I have an exponential function divided by a trigonometric function. These are, and I said this before, these are actually a little bit easier because there's not as much simplification that comes out of them as long as we know the derivatives of the types of functions that we're working with. So f prime is 3e to the x. Very nice. It stays the same. And g prime is negative sine x. The negative sine x, as you're using this, specifically if cosine is a denominator, just remember that you're going to have to probably change that to a positive because you'll be subtracting that derivative within the quotient rule. Also, an additional note, and you'll see the simplification highlight here, factor common terms. Whenever we have an exponential e to the x within our quotient rule, a lot of the times we're going to have to factor a common term out because that stays the same. So there's going to be sort of two versions of that within the problem, whether it's f prime or f or g prime and g. And those will stay within the numerator, but I'll have to factor out the common term within it. So we'll just kind of jump right into it here. Here's f prime g minus g prime f all over g squared. The only bit of simplification right here is that I have a minus a negative sine x, right? So I'll change that into a plus, and I just move the 3x in front of the sign, which is fine because it's multiplication. So 3e to the x cosine x plus 3 to the x sine x all over cosine squared. What I notice is I have a 3e to the x in both terms on the numerator, and so that's where I'll factor that common term out. I'll come all the way out in front. I get 3e to the x cosine x plus sine x all over cosine squared. No other simplification that I can do, and so that's the end. So this is something I'd like you to write down. This is something that when we do have either a quiz or an assessment on the quotient rule or really any type of derivative, these are some simplification guidelines that we need to know. We're going to combine like terms, factor any common terms out. I don't want any negative exponents within our final answer. And doing that typically means we need to simplify complex fractions. So these are sort of big four simplification guidelines that we'll work through as a class that we'll use to try and get to the most common answer within our class. Okay, so at the end of this video, what we're going to do is take a look at the remaining trig functions. So we know the derivative of sine, we know the derivative of cosine. What we don't know is derivative of tangent, cotangent, secant, and cosecant. And what's nice about those for remaining functions is that we can simplify those, or I guess we're technically kind of expanding them into a ratio of other trig functions, specifically trig functions that we already know the derivative of, which is sine and cosine. For example, we know that f of x is equal to, we know that tangent of x is equal to sine over cosine. Turning that into a fraction, turning that into a quotient, means I can use the quotient rule. And if I know the derivative of the pieces, then I can get to the derivative of the overall function. Eventually, we'll use all the four of these enough that you won't have to go through this process every time. So this is sort of the discovery of the derivative of tangent, cotangent, secant, and cosecant. But if you do get into a pinch and don't remember what the actual derivative is, this is how you get to it. So this is a really good first step for us with these. So I'm just going to kind of show this up here, and we can move through it. We'll start with, sine of x being f and cosine of x being g, and I'll take the derivatives. Again, just being careful because you'll see a lot of like terms here because we know the derivative of sine is cosine, derivative of cosine is negative sine, and so we'll be multiplying a lot of the similar functions together. But it actually really helps us out in the end, right? So the first part, f prime g is cosine times cosine, derivative of the top multiplied by the bottom, minus negative sine times sine, derivative of the bottom multiplied by the top. That creates a squared cosine and a squared sine. This hopefully is jumping out on the page at you. Cosine squared plus sine squared of x. That is our Pythagorean identity. This whole thing, right, is actually equal to 1. And once that goes away, I get 1 over cosine squared. And the last bit of simplification here is knowing what 1 over cosine is. So 1 over cosine is secant, and 1 over cosine squared is just secant squared. And so what we know and what we can jump to, we don't have to do this every single time, right, is that the derivative of tangent is secant squared. Okay, I meant to cover this up, but that's okay. What I want you to do is pause the video at this point and see if you can get to the derivative of cotangent using the exact same method that we just did for tangent. So take a minute, pause the video, see if you can simplify cotangent into its ratio of sine and cosine, and then move through the quotient rule in order to get to the derivative of cotangent. Okay, hopefully you did that. Hopefully you had a chance, and hopefully you were successful. Here is the answer, and here is the process. So cotangent is cosine over sine. It's a very similar process. The biggest difference here is that the numerator and denominator, once we do the sine times sine and cosine times cosine, I have both a negative and a minus here. The trick is just to factor out a negative, factor out a minus. Once I do that, the minus or the negative goes all the way in front of the fraction, and then it actually works out almost exactly the same way, where I have that sine squared plus cosine squared in the numerator. That becomes a 1. I have a negative 1 over sine squared. 1 over sine is cosecant. 1 over sine squared is cosecant squared. And so the ending is negative cosecant squared. My final two, secant and cosecant. Here is my derivative of secant. This one works out even nicer because I know that secant is 1 over cosine. Well, the derivative of 1, which is a constant, is 0. So the top actually simplifies itself really nicely. So you can see how this works out. 0 times cosine, this will go away completely. Derivative of cosine is negative sine. So again, this changes to a positive sign. So I just end up with sine over cosine squared. Here's the trick for secant, and which will also be the trick for cosecant when you try that one, is this can be simplified into 1 over cosine multiplied by sine over cosine. That's really nice because if I don't have to use a fraction here, I don't want to. And so this is the most common version of the derivative of secant. 1 over cosine is secant x, sine over cosine is tangent of x, and so you actually get the derivative of secant is equal to secant x tan x. And again, you can jump right from here to here at this point as long as you understand that process and you can know that derivative. You can certainly work through this quotient rule and get to that derivative if you need to, but we don't have to necessarily. Okay, last try on your own for today. Why don't you try and do the exact same thing for cosecant? Take a minute, pause the video, and once you're done, play the video again and I'll show you the answer. Very similar steps. Go for it. Okay, let's show the answer here. So 1 over cosecant is equal to 1 over sine. Again, I have that derivative that's a constant. The numerator that's a constant, so its derivative is 0. The numerator simplifies nicely. I have, again, almost the exact same simplification process here. I get a negative cosine. That does not change the negative because the derivative of sine is positive cosine. And then from there, negative 1 over sine x multiplied by cosine over sine, just splitting up this fraction so that I can make negative cosecant of x multiplied by cotangent of x. So we've got our final trig derivative. The derivative of cosecant is negative cosecant cotangent. Okay, so that is actually it for today. We did a couple of different versions of the quotient rule. We looked at all different types of functions that we could use, and finally we ended up with all 6 trig function derivatives. Here they are. This is something, again, you should take special note of. If you're keeping that log of different derivatives and different derivative rules, this is something that you should put together or put in there. Okay, you need to know all 6 of these without being told them, without being given to them. Okay, so you can either derive them from doing the quotient rule for at least the bottom or the 4 that we just did today, or you just need to know these moving forward. Okay, so these are the 6 new trig function derivatives that you have to work with and to use within any type of problem that we're working with from here on out. All right, guys, I hope this was helpful, and I will talk to you soon. Please let me know what questions you have. Look on my Malvern for homework.